Section 3.6 is kind of a big section, so I broke it into two different videos. In this second part, we're going to kind of pick up a couple special cases. The process will still be the same for the most part, but there will be a few kind of unique things that happen in this section. So the first example that I want to look at is f of x equals a function like this. Again, the directions are going to say graph, and what I want to do is kind of approach this with our list from yesterday and show you what happens and how to rectify the situation. So the first step we're going to do is X-Intercepts. The top over the bottom set equal to 0, and the bottom clears out when you multiply through by the bottom, and you're just left with the polynomial set equal to 0. So we're going to factor it and set each quantity equal to 0. So that means x equals 4 and -3 are my x-intercepts. So far, it's looking normal. Y-intercepts, I'm going to plug in 0 for x. So I get -12 over -4, which is a +3. That's my y-intercept. And then my vertical asymptotes, set the denominator equal to 0. So x equals 4. And here's the first time where we start to think something weird is happening. I take my horizontal asymptotes, the limit as x goes to infinity, and I'm going to divide everything by the highest power of x in the denominator, which means we're going to divide everything by x. So let me write the original function, and then we'll divide. So this is going to be the limit as x goes to infinity of x squared over x is x over x is 1, 12 over x over x is 1, and 4 over x. Now look at what happens. This right here is the unique part. So these guys are going to 0 because 4 over infinity is 0, 12 over infinity is 0. And so what I'm left with is, if x is really big, then this is going to be a really big number. That's my x value, minus 1 over 1, which is a really big number, right? Because if you subtract 1, that doesn't really do anything to a million. And if you divide by 1, that doesn't change the value. So this limit is actually going to infinity. It's getting bigger and bigger with as x gets bigger. So that's the first place where we go, how do I have a horizontal asymptote at infinity? Okay, that means that there's no horizontal asymptote. Okay, and that's the clue that you want to take a look back up top and see if maybe you missed something going on. So I'm going to look at this original graph. And the other place you can see kind of something weird is start drawing this. Let me show you what it looks like. I'm not going to go all the way down this path every time this happens, but in case you miss it, I want you to see what it looks like. So my x-intercepts are 4 and -3. 4 and -3. My y-intercept is +3. My vertical asymptote is 4. This is a huge red flag right there. This is big red flag. Why? Because I've got an x-intercept on a vertical asymptote. That's illegal. Okay, so there's something very wrong here, and that is your indicator. And if that happens, what you missed is that there is part of this original function that reduces. So I'm going to do this in red because we're going back in. Let's factor this right away. This factors as x minus 4, x plus 3 over x minus 4. Look at this. These cancel. You did that in Algebra 2. You reduced your rational functions. And that means that this is actually a graph of x plus 3. It's not a rational function at all. It's actually a line. F of x equals x plus 3. That's y equals mx plus b form. So this is not the right road, okay? So let's go ahead and graph this. X plus 3. Now, how do I avoid doing all this work before I figure out that I missed something? My recommendation is to factor everything first and take a look at it. So first, I would factor it and say, does anything cancel? And then go from there. All right, so what we're graphing is f of x equals x plus 3. Okay, y-intercept of 3, slope of 1, so up 1 over 1, and it looks like this, and this way. Okay, so there we go. Now you're saying to yourself, wait a minute, but I mean, this isn't a line. That has to be different than a line, and you're right, it is different. What still applies in this situation is that the domain is still restricted. So the domain is still everything except x equals 4. So in essence, this vertical asymptote is still in play. And what that does to the line is at x equals 4, on the line, it makes a hole. Okay, it's not really an asymptote per se because the graph isn't growing towards that dotted line, but it does make a hole in the graph. And so your final answer would look like just your line, like this, with a hole in it. And you don't have to draw this, I just did that for a visual. And a hole at 4, okay? So what I call these special case problems, these are holes, okay? That's what these are. It's when your denominator cancels with your numerator and creates a different kind of function. Now, it doesn't always have to create a line. It could create a parabola, it could create another rational function, but the deal is you graph whatever you're looking at after you cancel it, and then you just find where your hole is and put that in at the end. Okay, so that's our first kind of special case. The second involves a different kind of asymptote, and these are problems with slant asymptotes. All right, so let's look at one of those. Here we go. Let's go through our steps. Actually, since we just learned that, you could go through a lot of work and have it not be worth anything unless you factor first, let's do that. Let's look at it in both ways and make sure we don't miss anything that cancels. Okay, so I factored it, nothing up here cancels with nothing down there. So that means that this is not a whole problem. So I am going to go through my procedure. So first, I'm going to find my X-intercepts. Then I'm going to wipe out my denominator. So x equals 4 and -3. Those are my X-intercepts. My Y-intercepts are my next step. I'm plugging in 0 for x. I'm going to plug it into the top form. You can plug it into the factored form if you want. Doesn't matter. You get the same answer. I get a -6. My vertical asymptotes. Set my denominator equal to 0. And my horizontal asymptotes. I want to use the multiplied out form for the limit, as we saw in the last video. And I want to divide everything by x, because that's the highest power of x in the denominator. So I'm going to get x on top. X over x is 1. 12 over x. X over x is 1, and 2 over x. So look at what's happening here, the same thing that happened with the wholes. So I'm on alert that there is something different, again, happening here because of this. These guys go to 0, and I'm left with a big number. That's what this x is. I plug in a big number, that's just a big number. Minus 1 over 1. Well, that's just a big number. So we say that that limit goes to infinity. So that means that there's no horizontal asymptote. Now, I'm on alert. Did I miss a hole? No, I didn't, because I checked that before we went. There's no hole, there's nothing that cancels. So what that means, if there's no hole, is that there is possibly a slant asymptote. How do you know if there's a slant asymptote? It is possible to have a slant asymptote if the power in the numerator, the top, is exactly 1 more than the power in the denominator. So let's look at our original function. The power on top is 2, and the power on the bottom is 1. So this is exactly 1 more than the denominator, and that's what tells me I need to look for a slant asymptote. Okay? How do you find slant asymptote? I am so glad you asked. You find it by doing, wait for it, long division. Ta-da! That's the application from section 3.3. All right, so let's take a look at it. Here's my function. And I told you, you can always write a rational function just as a fraction like this, or you can actually divide it out. So what happens when we divide it out? I put the top underneath. I put this out in front. And remember, fill in zeros for missing powers of x's. In this case, because this is a linear term right here, you could use synthetic division. But I am not going to. I'm going to use long division. And I'm going to say, what do I divide the first term by to get the first term? Well, that's going to be, I need an extra x. I'm going to take that x, I'm going to multiply it out. Okay. I'm going to subtract, so I'm changing both of the signs. So these two cancel, and I get a negative x plus a 2x is a positive x minus 12. Then I say, what do I need to multiply x by to get x? Well, they're the same already, so all I need is a 1. Now here's the cool thing. This is just crazy. It does not matter what the remainder is. So once you finish this last place on your division, you're done. You throw y equals in front of this, and this is the slant asymptote. Isn't that crazy? I can't even believe it. Like, who in the world discovered this? It's stunning. So the remainder, I mean, you can find that if you want. You can multiply by 1 and x plus 2, change the signs, and your remainder is negative 14. But that doesn't mean anything for the graphing. It's just this part. And this slant asymptote is always going to be a line. Why? Well, because the power in here is exactly 1 more than this. So all that's ever left is a linear term, a power of 1. Interesting. All right, so let's draw this guy and see what happens. My x-intercepts are 4 and negative 3, and my y-intercept is -6. 4, -3, and -6. Okay. And my vertical asymptote is -2. I don't have a horizontal. By the way, you'll never have a horizontal and a slant together. The slant replaces the horizontal. And my slant is a line, so I'm graphing this line. My y-intercept is 1, so I'm starting here at 1, and then I'm going to go up 1 over 1. So it looks like this, okay? Now, what that slant does, it's like a horizontal, only it's just tipped a little. Do you see that we still have 4 sections? We have 1, 2, 3, 4 sections, right? It's just like it's just skewed up a little bit. And so we graph these the same way. There's a swoosh, either in the top or the bottom here, and either in the top or the bottom here. And you just have to decide which is which, right? The points are going to guide us. And you can always plug in points if you're not sure. But look, here's 2 points. Ta-da! So the graph must be in this. Now remember, it grows towards the asymptote. So this is going to go like this. This is, oh, that's a bad drawing, but this actually is growing out. So it's like a swoosh, but it's super wide. Okay? I don't know. I'm not super great at drawing, but that's the idea. Okay? It is kind of roughly curving. Maybe that's a better drawing. It is roughly curving, but it's just curving really, really wide. Okay? And then over here, if I'm upper left or lower left, well, there's a point right here. So that tells me that I'm in this section right here. Okay? And that's it. If you're unsure, you can plug in some points. But they operate, once you find the slant, they operate a lot like the very first problem we did in section 3.6 in the last video. Okay, try some of those and we'll do some extra practice in class.